So the rock mechanics, as we keep talking about, is a discipline that uses the principles of mechanics, which we have described earlier, to describe the behavior of how our rock is. So then, the normal construction material, taking for example your concrete slab, your tile, your glass, your wood, all of these materials have particular behavior. Your steel, your iron rods, they have certain behaviors that they exhibit. And these behaviors are such that we say they are continuous. Continuous in this sense means, let's take, for example, you buy a louver blade. The louver blade, is it supposed to have a crack? No. And so if I have any material designed for a particular purpose, that material should be continuous, meaning there shouldn't be any discontinuity in it, no cracks or any event that will render it useless. So if I buy a tile, a box of tiles, and I open, there are 10 pieces inside, and I open or 12 pieces, and then about 4 of them are broken, I am likely going to return it to the owner for a replacement. And so we say construction materials are supposed to be continuous. And then homogeneous, here we are referring to the materials that were used in making it are uniformly mixed. We don't have certain portions of it having more content of the various components that were used in making it. Then at another point, we have a very small component of the material. No. So take, for example, you are preparing, I don't know how many of us have tried gobe. If you have ever eaten some before, or you've seen them prepare it before, can we describe the things or talk about the ingredients or the things you see that make up the gari and beans people say? I want to explain the word homogeneity here. So let's use plain rice and stew, okay? So plain rice and stew means we are having two components here that we are using in our meal. One is the stew, and then the second one is the plain rice. If I am talking about homogeneity here, it means the stew you give me, I am trying to mix that quantity of stew equally around the entire plate of rice. If I have that mixed, such that if we are two eating and one is sitting at the opposite side of the plate, and I fetch a spoonful of rice, and you also fetch a spoonful of rice, and we are to test the quantity of stew you have gotten and the quantity of stew I have gotten, provided we all have equal spoons, and then the particles of rice we have fetched are the same. What do we expect? We don't want to see any cheating. And so the material or the content, which is the stew and the rice, are uniformly mixed. So there's no cheating here. But then when we come to our normal construction material, that is how it behaves. If I am preparing, take for example, a glass, I know that if I put certain elements together in their right proportion and mix them thoroughly, I am going to get a piece of glass. And that glass will stand the test of time in the market. And so I say the particles that came together to give me that piece of glass are uniformly mixed. And so I would say it is homogeneous. So if I have a cup of tea and I have my Milo, my needle or milk or whatever, and they are uniformly mixed, at the end of the day, they should have a common color. You don't see one side being brown with Milo and another side being white because of the milk. No, that is not homogeneity. And so our normal construction materials that we human beings are able to define its properties have these behaviors. They are continuous, they are homogeneous, and then they are isotropic. Isotropic simply means when I test the strength of this material in a certain direction, in any direction, it should be the same. So if I fetch or pick a spoon that has been designed in the factory. Maybe it is the handle, and I test for the strength of the handle along it. I should get the same property as if I am testing axially or laterally. They should have certain properties in all directions because they were uniformly mixed, and so their properties are the same in all directions. That is isotropic behavior. Then, since we are the same, uniformly mixed, and our strength properties in various directions are the same, then it means that if I apply a force on you, you are going to respond proportionally to the force I am going to apply to you equally. And that is linear elasticity. And so we cut it short and say chili, continuous, the C for the continuous, H for homogeneity, I for isotropic, L for linear, and then the E for elasticity. So if you want to remember it quickly, we say chili. Then the properties of man-made construction materials are known and controllable. So take for example, we have cement in various grades and strengths. And so if we are going to manufacture cement, we will know what properties of the cement we should put together to give us a certain grade of the cement. So if we are looking for a strength of 30, 32, we know what to put together to give us that. And in the same way, if we are looking for a grade of 42.5 or whatever, again, we will know what to do to get that. And so we are always able to control them, and the properties in there are known. Unlike our rock material, which they say is complex and difficult to define, it is so because they are discontinuous. You look at the face of an open pit wall, and you have cracks all over, fractures all over the surface. So that material is not continuous, it is discontinuous because of the faults and then the discontinuities you see there. Then the materials are inhomogeneous or they are heterogeneous. Inhomogeneous simply means the various components that came together were not put together and mixed by man. Take, for example, igneous rock. We said that it's as a result of molten magma. And so when the eruptions occurred and we obtained the magma, it was as a result of various rock materials that were melted, and then we got a magma. But as to how they were mixed, no human being was standing there to use a ladle to stir this magma to ensure that the properties within this type of material that will be formed should be the same. No, there was no control. And so it did that and did the cooling by itself naturally. And so you don't expect the properties and the materials that came together to be of the same proportions at every section of the rock sample you shall be holding in your hand. So if I have a rock sample of this sort, I may have more of phyllite on one side. I will have a certain portion having conglomerate on one side. Then I'll have a bit of schist on the remaining side. But all of this together, mixed together, maybe gave me a rock type which is called A or B. And so if I have that rock type and I call it igneous rock, it is as a result of certain minerals coming together, but these minerals were not in their correct proportions or equal proportions. Then anisotropic, because this material was not in measured proportion and uniformly mixed, if I test the strength of the rock in one direction, I will get different strength values than if I test it in another direction. And so it is anisotropic. And because these properties are not the same, when I subject it to load, this particular material within the igneous rock will be responding to the load I'm applying differently, whilst another portion will also be responding to the load differently. So at the end of the day, I am not, or the result is not linearly elastic. So this is a picture showing how our normal rock material look like on the surface in the pit. I don't know, maybe in your case, the type of material you deal with is different. So even if it's a soft material, you still will see these cracks. They are very common with the surfaces we've been working all the time. So we say conventional material are chili, and this is Diane. These ones are not words, so you may decide how you can call it appropriately to remember what we just talked about.